All right, so this idea of this not constant cross-sectional area, for Cartesian coordinates, like I said, you have the homework problem to deal with, but there's also, it also comes up in non-Cartesian coordinate systems. So if we look at the next slide, so okay, there's cylindrical coordinates, there's spherical coordinates. I mean, I think you've dealt with these before, so we don't have to spend too much time on them, but just kind of want to point out what it looks like to deal with this non-constant area. So for cylindrical coordinates, we're going to say, I've got some radial coordinate, r, right, that represents the radius. I've got some r in, and I've got some r out. So in this problem, as I've drawn it, the domain is from r in to r out. It's hard to see in this, but let's say that's the only solid part that we're considering. It's like a tube, right? So you have r in and r out. We could also potentially have heat flow in this direction called theta, right? We aren't just limited to having heat flow in the r direction. We could have it in theta, in the circumferential direction. We could also make this into like a 3D system where we've got some axis here down the middle of the tube, and this would be like, say, the z coordinate, right? So it's still a 3D geometry, but it's the third dimension's going kind of into the page. Right, so okay, so cylindrical, you could do this. You could have heat flow in r, in theta, or in z. For a lot of the problems we're going to look at, it's just r. But in this case, it's not clear what the cross-sectional area is for conduction, especially in r. Right, as you go out in radius, that area is changing. So just by having a different coordinate system, you have kind of this area factor. Same thing goes for spherical. Right, you have, again, this radius here. Maybe we have some angle phi that we have to deal with. And then down here, you have maybe an angle theta. So again, three-dimensional coordinates, but similarly, the area is going to be changing. So you want to be comfortable moving from these different coordinate systems, right? You be comfortable in Cartesian coordinates, be comfortable in the other coordinates as well. Okay, so one more thing on this, and then we'll kind of get into the actual methodology. So if we're doing analysis on Cartesian coordinates, let's take this example. It's some long rectangle, some bar, and we have heat flow that's going in this surface, and let's call this coordinate x. Right, we're going to need to be thinking about not just the cross-sectional area, but when you get into the methodology, you see that we have to define the boundary conditions. So we have to think about what's happening on the left-hand side, what's happening on the right-hand side, because that's what fixes the problem to a certain solution. So here we've got Cartesian coordinates, left and a right boundary. Here we have our AC, right? That's our cross-sectional area. That is not changing as a function of x for this particular example. Here on the very end, we have AS. So draw that distinction in your mind that the cross-sectional area and the surface area could be different, right? So that's for Cartesian coordinates. If we go back to cylindrical coordinates, right, we could take our radius here. Here's this circle that I've drawn is supposed to be our control volume, which we'll see how that kind of works out. But this control volume, right, this area here is our cross-sectional area, right, and that is a function of r. Out here, this is our surface area. So you can see how the surface area is different from the cross-sectional area, right? It's fairly obvious, but I just want to make that point because it will be confusing later, okay? Yeah?
Is this like a hollow cylinder?
Yeah, the question was, is this a hollow cylinder? Yes, so I'm trying to draw this as like this. Let's see if I can. So this, everything in here is solid, right, like this. And then the control volume is basically like taking an infinitely thin slice in the r direction and doing an analysis on that.
Okay.
So when we come to enforcing boundary conditions, we'll kind of go through that. But basically, you take the area of the inner surface as one boundary condition, the area of the outer surface is another boundary condition, and you enforce both of them. Okay. Any other questions on this? coordinate system kind of area stuff? Yeah, so remember, I mean, this is a good question, right? Go back to Fourier's law. So if we say q dot is equal to minus k dt dx, right? As we go through this, we're going to see, in many cases, at least for the simplest setup, q dot double prime, or q dot at least, is constant, right? Q dot, the total heat transfer is constant. So if that's true, and say the area is changing, you could write this as this, q dot equals minus k ac dt dx. So if ac is a function of x, and q dot is constant, then the only thing that's left to change is the temperature gradient. Right? And actually, the first problem on the homework, I want you to do this, right? I want you to look at Fourier's law, look at the conditions that are given to you, like area is changing, conductivity is changing, heat flux is changing. And from that information, figure out how that relates to dt dx. Right? So that's a really core concept of heat transfer, is figuring out how q dot relates to dt dx, given the other stuff. But the governing law is always the same. Right? Other questions? Okay. Right, so let me just give you the kind of the takeaways here. So for Cartesian, we'll say normally AC is equal to AS, generally. Not always true, right? As in the homework that you're going to do, but if it's a rectangular system, that's usually the case. For cylindrical, normally AC is not equal to AS. AC is a function of R, and so that would be A cylindrical is equal to 2 pi RL, right? You all remember the equation of a cylinder, but every semester there's somebody who doesn't. A spherical is 4 pi R squared. So when you go to plug this into your control volume, this is what you use. Okay, so maybe it's not clear yet how you're going to use this, but let's get there now, okay?